Welcome to today's Explainer. I am so incredibly excited to share this one with you because we're taking a mind-bending journey today. We're going to start with the everyday, completely normal things we can touch, the screen you're looking at right now, or the chair you're sitting on. And we are going to travel all the way down to the most terrifying, intensely crushed objects in the entire universe. It is literally an epic cosmic battle between the fundamental forces that dictate how our reality works. So what happens when you squeeze matter infinitely? I want you to start by picturing something kind of crazy. Imagine taking everything around you right now, your desk, your house, maybe even your whole neighborhood, and putting it into a giant cosmic vice grip. Imagine squeezing it relentlessly, crunching it all down into a smaller and smaller space, like packing the ultimate snowball. What actually happens when you just keep crushing matter deeper and deeper? Does it eventually break? Does it push back? Well, check out this number. 99 point, a whole lot of nines, percent. That is exactly how much of an atom is just completely empty space. What feels totally solid to you, like when you knock your knuckles on a wooden door, isn't actually filled space at all. It's really just microscopic forces pushing away from each other, kind of like when you try to force two opposite magnets together and you feel that invisible resistance. The actual solid center of an atom is unbelievably tiny compared to the fuzzy electron cloud buzzing around it. And because of this vast amount of empty space, matter can absolutely be crushed. The ultimate cosmic pressure war. You can think of a star's entire life cycle as a giant heavyweight wrestling match. Gravity is constantly trying to crush the star inward, while heat from its core pushes outward. But when the star finally runs out of fuel and cools down, a bizarre quantum defense kicks in called degeneracy pressure. Basically, this is the quantum rule that electrons absolutely refuse to share the same space. Think of electrons like extremely stubborn siblings who flat out refuse to share the exact same bedroom. When gravity squeezes them too hard, they push back, creating an almost indestructible shield that holds the entire star up. And the craziest part? It works even when it's colder than anything you can possibly imagine. The paths of stellar death depend entirely on their starting weight. This cosmic wrestling match plays out in a few different ways, and the path a star takes when it finally dies depends completely on how heavy it was to begin with. As gravity eventually overpowers their internal pressures, different weight classes of stars hit different physical floors, basically shattering into completely different wild space objects. White dwarfs, squeeze diamonds. Let's visit the very first floor of our cosmic battle, which is where the smaller stars end up. After their outer layers puff away into space, the leftover core is supported entirely by those stubborn, pushing electrons. We call this a white dwarf, and here's where the physics gets deeply weird. Adding more mass makes it smaller. Because of how quantum physics works, if you pack more stuff onto a white dwarf, it doesn't get bigger like a snowball would. It actually shrinks. It's like having a suitcase that gets physically smaller the more clothes you stuff inside it. As it cools over billions of years, the carbon inside crystallizes, and it literally becomes a giant Earth-sized diamond just floating out there in space. But let's look at the ladders of extremes when it comes to density and magnetic fields. What happens if a star is heavy enough to completely shatter that stubborn electron shield we just talked about? Well, the electrons get shoved right into the protons, and the core goes into a catastrophic freefall. It collapses inward at a quarter of the speed of light. It only stops when it hits a brand new, infinitely denser floor, violently bouncing back in a massive explosion that we call a supernova. Neutron stars, giant atom cores. That violent supernova explosion leaves behind what's called a neutron star. Here, the incredibly strong cosmic glue that holds atomic nuclei together fiercely pushes back to stop the collapse. It is really hard to wrap your head around how dense a neutron star actually is. So, try this. Imagine gathering up all 8 billion humans on Earth. Now imagine squishing every single one of us down so tightly that we all fit inside a single, tiny sugar cube. That is what nuclear density looks like. Because it is packed so tightly, a neutron star isn't even made of normal atoms anymore. It is essentially one single giant atom core stretching for miles and miles across. Because of this, just a single teaspoon of neutron star material scooped up from its core would weigh a mind-blowing 5 billion tons. 5 billion. That is literally like trying to balance an entire mountain range inside your morning cereal spoon. Pulsars and extreme cosmic magnets. When these massive stars collapse, they also spin up super fast, creating absolute monster magnetic fields. Think of an ordinary refrigerator magnet holding up a drawing in your kitchen. A magnetar, which is a very special hypermagnetic kind of neutron star, is trillions of times stronger than that little fridge magnet. If you put a normal, perfectly round atom anywhere near it, the magnetic pull is so intense it literally stretches the atom itself out into a long, thin needle shape. These things are incredibly, terrifyingly powerful. The magnetic field is so violent, it can literally crack the star's rigid outer crust. In fact, a 2004 magnetar flare compressed Earth's ionosphere from 30,000 light-years away. Think about that for a second. This magnetar unleashed a giant flare of explosive energy. The blast traveled 30,000 years at the speed of light across the galaxy, and when it finally hit Earth, it possessed enough force to physically squish the very top of our atmosphere, from halfway across the Milky Way. Black holes, the final floor. So what if the starting star is the absolute heaviest of all? Let's break down our heavyweights. A white dwarf, born from a star less than 8 times our Sun, is eventually defeated by extreme weight. A neutron star, from a star 8 to 25 times our Sun, is defeated when gravity actually turns the star's own internal pressure against it. But a black hole, born from a star over 25 times the mass of our Sun? Nothing we know of defeats it. It's no longer even made of matter as we understand it. It's just mass, spin, and a one-way trapdoor, where space itself gets dragged inward, like water down a cosmic drain, faster than the speed of light. Now, there is a really huge misconception here that we need to clear up. The strong force doesn't fail, gravity just outvotes it. When a black hole forms, the super strong glue inside the atoms doesn't break or give up, it just hits its absolute physical maximum limit. Gravity, on the other hand, never stops growing. It's like an unstoppable playground bully. Matter fights back absolutely as hard as the laws of physics will allow, but gravity, with all that extra mass, just pushes right past it and wins the vote. Which leaves us with the ultimate question: what mysteries lie hidden at the Planck density? If gravity wins the war, does matter crush down into a literal, infinitely tiny dot? Most physicists actually think infinite compression sounds totally wrong. It's usually a sign our math is breaking down. So I leave you with this incredible mystery. If we could somehow zoom in smaller than anything we could ever possibly measure, what actually stops the crushing at the very bottom of our universe? Do things eventually bounce back? Are there tiny vibrating strings holding it all together? We are still searching for the answer. And honestly, that's what makes this so incredibly fascinating.